I'm Mark Arenes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 19. Calculate how many Sundays fell on the first of a month during the 20th century. We're given that January 1st, 1900 was a Monday, and are tasked with counting the Sundays which happen to be the first of the month, starting with the year 1901 up to the year 2000 inclusive. We can jump right in and run this calculation directly. If we use a language that has a good built-in date library, we don't have to do any of the date or leap year calculations ourselves. Let's work in Julia today. Julia has a dates module as part of its standard library, but it's not imported by default. There are two ways to import modules in Julia. The simplest is with the import statement. Import simply pulls in a module from somewhere else, introducing the name of the module into the current scope. If we write import dates at the top of a Julia file, then this defines a global variable called dates, which is a module. Inside that module are several structures and useful functions, and we can access them as qualified names. However, Julia also provides a using statement. Using pulls in the module just like import, but then it also introduces some of the names from the module into the current scope, so that we can refer to them unqualified. If we don't explicitly specify which names we want introduced into our current scope, Julia gives us the module's export list, which is a curated list containing the public API as defined by the library author. We'll use the using form for our work today, so we can refer to the structures and functions in the dates module unqualified. Let's write a function to compute the number of Sundays at the first of a month on a given interval. It takes two arguments, a start date and an end date. Inside our function, we initialize our count of Sundays to 0. Then we start iterating as long as the current date is less than or equal to the stop date. Inside the loop, if the current date is the first of a month and happens to be a Sunday, we increment our counter. Next, increment the current date by 1 day. Finally, when we're done, return the number of Sundays. Outside the function, we simply call our helper with the given date range and print the result. There are several things to note here. Date is a composite type defined in the dates module, which stores information about a particular day on the calendar. Composite types in Julia are defined using the struct keyword and are sometimes called structures. Julia has a different data model than its sibling languages Python and Ruby, in that Julia doesn't have classes and interfaces per se. In Julia, there are, broadly speaking, two kinds of types, abstract types and composite types. Composite types are defined to be a product of several fields, similar to a struct in C, and can optionally inherit from one abstract type. Abstract types, on the other hand, are defined using the two words abstract type. They have no body and no implementation and merely serve as signals to other functionality. An abstract type may optionally inherit from one other abstract type. Of course, simple data structures aren't powerful enough to represent abstractions in a high-level language like Julia. Generally, we want the implementations of our data types to be hidden. In Python or Ruby, we would write methods on a class to expose a public API for that class. Julia doesn't define methods on classes, but instead treats them as standalone objects in their own right. Nearly every single function in Julia is a multi-method. That means that nearly every function in Julia can implicitly have several overloads that are resolved dynamically based on the types of their arguments. For instance, the built-in string function, which converts an arbitrary value to a string, has 20 overloads in the Julia standard library. When we call string, depending on the type of the argument, we'll call one of the 20 method implementations to convert that specific type to a string. For context, the built-in plus sign method, which is used when we invoke the infix plus sign operator, has over 150 different methods defined on it. So when you want to define a data type in Julia, you define it as a struct or abstract type, and then you define your public API as several standalone functions. If the function names overlap with those defined elsewhere, then the function simply has additional method overloads to consider. This is where the day and day of week functions come from. In other programming languages, we might have written these functions as methods on a date class, but in Julia we write them as standalone functions on the dates module. In fact, even these basic accessors are multi-methods. Julia defines two overloads for the day and day of week functions. If you pass a date object, it returns the day of the month and of the week, respectively, referenced by that date. However, if you pass a plain integer, then the function interprets it as a number of days, where day 1 is January 1st of the year 1. To add to a current date, we simply use the plus sign on the date object and a day object, which is a type of date period. All functions in Julia are open, which means future programmers can always add new overloads to an existing method. Even though the plus sign method is defined in the base module, the dates module is free and encouraged to add new overloads to it. It seems like a bit of a waste to iterate over every day when we only need the Sundays. After all, ideally we should be able to jump ahead by 7 days at a time, since we know that's how often Sundays occur. The only problem with that is that we have to have a Sunday to start at. Let's add a parameter to our function indicating an existing Sunday. We'll start iteration from there and count out by 7 days instead of 1. We add an additional check inside of our loop to make sure the current date falls within our desired interval, since the known Sunday may be outside of the interval. In our problem description, we're given that January 1st, 1900 was a Monday, so we know that the first Sunday in 1900 was January 7th. We pass that date as our first argument to count Sundays. Remember that, as we discussed in a previous video, we should keep local variables like known Sunday inside of a let block rather than letting them take module scope automatically. It won't actually change the behavior of the program in this case, since there are no soft scopes to contend with, but it's still good practice nonetheless. We can aggregate this a bit more. The start and stop dates are really an interval, so let's write a custom data type that represents this concept in our code. We'll call this type interval, and it should be constructible, not abstract, so we'll make it a struct. When defining the body of the struct, we generally only specify the fields. In our case, an interval of type t consists of a start value and a stop value, both of type t. Next, we define accessor methods to get the start and stop positions from our struct. In Julia, there's no way to make fields on a struct private. Anyone can always access them using the dot notation seen in many object-oriented programming languages, but it's generally considered poor form to treat them as a public part of your API. So to make it clear that these are public fields, we provide accessors to them. There's nothing else special about these accessor definitions. Julia allows one-line function definitions to be written using this more compact form, but it's otherwise equivalent to the written-out form we've been using up to this point. Next, we define a method called base.n. This method takes two arguments, an element and an interval, and returns true if the element is contained within the inclusive bounds indicated by the interval. There are several things to note here. First, the base.n method is not a function we just made up. As I said, all functions in Julia, with the exception of a handful of bootstrapping primitives, are subject to multi-method dispatch. The base.n function is Julia's general-purpose container inclusion function, with over 35 method implementations in the standard library for types ranging from arrays to dictionaries and so on. And we can add an implementation of this method for our type as well. In fact, the in function is an operator in Julia, so we can call it using infix notation. Additionally, our interval type is generic. We never specifically mentioned dates. In fact, we didn't really commit to any defined interface. Our method implementation for base.n is duck typed, which means that it can simply work correctly for any type which implements the functions we need. In our case, all we need is the less than or equal to operator, which, you guessed it, is subject to multi-method dispatch. That means that, while we wrote this interval to work with ranges of dates, it could also work with ranges of integers, floating point values, strings in lexicographic order, or tuples of any of the above. Finally, note that we also never wrote a constructor for our custom type. If you don't implement one yourself, Julia gives you a default constructor which takes all of its fields as arguments. We could have overridden this behavior, but in our case the default sufficed quite nicely. Next, we update count Sundays. Instead of taking a pair of dates as separate arguments, we take a date range as a single argument. Our while loop still checks that the current date is less than or equal to the end of the range, but we change our inner conditional to check that the current date is within the date range, using our base.n method implementation. Next, we construct an interval in our main block of code and pass it to the count Sundays function instead of two separate arguments. Now we've cleaned up our code a bit and gotten some practice with data structures in Julia. Let's simplify this code down to its bare basics so we can translate it into a simpler language. Let's pretend we don't have any date primitives to work with. We won't import the dates module and we'll do all the calculations ourselves. Let's start by writing a couple of helper functions. First, isLeapYear will take a year number and tell us if the year is a leap year. Every 4 years is a leap year, so our base condition simply checks whether the year number is divisible by 4. However, years divisible by 100 are not leap years, unless that year happens to be a multiple of 400. So we have to do a bit more conditional plumbing to make that work. Next, we'll write days in month. This function takes a 1-based month number and a year number and returns the number of days in that month. Julia doesn't have a built-in switch case statement, so we simply do this as a sequence of if-else statements. If the month is April, June, September, or November, then we return 30. If the month is January, March, May, July, August, October, or December, we return 31. Otherwise, we check if it's a leap year to decide between 29 and 28 for the month of February. Now we rewrite count Sundays. Instead of keeping track of the date in one variable, we store it in 3. A year number, a month number, and a day number. The month and day numbers are 1-based. Our known Sunday is January 7th, 1900, so these are our starting values. While the year is less than 2001, add 1 full week to the day counter. Then, if we've reached the end of the current month, increment the month counter and reset the day counter. When we do this, we might have landed on the first day of a month. If we did, increment the Sundays variable. Next, check to see whether we've reached the end of the current year, and if so, increment the year variable and reset the month value. At the end of the loop, return the number of Sundays we've counted. And finally, in our main block of code, print the total count. Now we have a working, fast, and most importantly, zero-dependency version of our Sunday counting program. Let's discuss our language of the week. We'll be solving this Project Euler problem in QBASIC, which is a stripped-down minimalist version of Microsoft QuickBasic. QBASIC is a dialect of the BASIC family of languages. In the 1970s and 80s, basic dialects flourished and positioned themselves as easy-to-use introductions to the world of programming. Nowadays, BASIC is mostly historical and used for recreational purposes, like what we're about to do. QBASIC is relatively straightforward, fitting a language designed for beginners. There's no mandatory main class or function like in Java or C#, you simply write your code at the top level. In terms of actual code, all the usual arithmetic operators work. Plus performs addition, minus performs subtraction, star performs multiplication, and / is division. The modulo operator is written as the word mod in all caps. In fact, you should probably get used to having a finger on the shift key because all of the language keywords in QBASIC are in all caps. Variables in QBASIC can be suffixed with a sigil indicating their type. Integer variables use the % sigil, long integers use an ampersand, floats use the exclamation mark, double precision floats use the hash sign, and strings use the $sign. If a variable is not suffixed with a sigil and has not been declared in advance, QBASIC assumes it's a single precision floating point value. Since dates are composed of integers, we'll only need the % sigil today. Assignment of variables is done with a single equal sign, common to many programming languages. Variables don't have to be declared explicitly. Provided you include a sigil to indicate the type, QBASIC will implicitly create the variable at first use. Conditionals use if and then and are terminated by end if. The condition of an if statement must be numerical and is considered truthy if it's non-zero. For switch case style branching, we write select case, and then we write each branch as case. Branches don't have implicit fall through like they do in C and C++, so we have no need for a mandatory break statement. Select statements are terminated by end select. Comparisons are done in the usual way with less than and greater than. However, of particular note are equality and inequality. Equality is done with a single equal sign like assignment, not a double equal sign like in C. This doesn't present a syntactic ambiguity, since assignment to a variable is a statement, not an expression, and thus can't be used in an if statement's conditional. Inequalities perform with a less than sign followed by a greater than sign, read as this value is less than or greater than that value. QBASIC doesn't have a designated Boolean type, so Booleans are indicated by numbers. By convention, the built-in Boolean operators use 0 for falsehood and -1 to indicate truth, since -1 is the number with all bits set when writing a 2's complement representation. QBASIC has 3 looping constructs. The first is for, which takes a counter, a starting value, and an ending value. The bounds are considered inclusive, and the body is run for each integer from the start to the end. A step can optionally be provided to go by more than 1, in reverse, or by a floating point value. For loops are terminated by the next keyword followed by the looping variable name. While loops take their condition up front and run until the condition is false. While loops are terminated by the wend keyword, short for while end. Do is a more general purpose form of while looping. Do loops start with do and end with the loop keyword. Without any modifiers, a do loop will simply run forever, or until exited with the exit keyword, which is the equivalent of break from most conventional programming languages today. However, a while or until modifier can be attached to either the do or the loop part to indicate a stopping condition. If the condition is placed at the end, then the loop is guaranteed to run at least once, as the condition is checked at the end rather than the beginning of execution. We can output a variable to the console with the print keyword. So far, all we've discussed is basic control flow, but QBASIC would hardly be a general-purpose programming language if it didn't provide us with some way of defining functions for programming in the large. Firstly, QBASIC provides ordinary go-to style branching. Labels are suffixed with a colon, and your program can go to a label at any time. All jumps of this form are unconditional, but they can be placed inside of if statements or other conditionals. On top of that, QBASIC provides a graduated approach to help get students of programming to think in terms of functions. A label can optionally be ended with the return keyword. If we use goSub to jump to a label rather than goTo, then QBASIC will remember where we came from, and a subsequent return keyword will jump back to that point. Note that this isn't a real subroutine, as any variables modified in the subroutine are in the same scope as the caller. In terms of actual segregated procedures, QBASIC provides 2 mechanisms: subroutines and functions. Subroutines are defined with the sub keyword, while functions are defined with the function keyword. Both subroutines and functions can take arguments. However, subroutines are always called as standalone statements, while functions are always called as part of a larger expression. Further, since subroutines are always their own statement and not part of any larger computation, they cannot return values. As such, subroutines are only used for side effects, such as modifying an input argument or printing to the screen, while functions should be used for computations that return results. As an example, let's write a function which checks whether its input is prime. Function names, like variable names, have sigils, and the sigil indicates the type of the return value. The return keyword only applies to goSub, not actual functions. At the end of our function, the return value is the value of the local variable whose name matches the function's name. So in our case, the returned value from our function will automatically be the current value of the local variable called isPrime %. We start that variable with a value of -1, representing true. Then we loop from 2 up to half the input. If we find a divisor, we set our return variable to false and exit the function immediately. If we reach the end of the loop without doing so, then our default return value of -1 gets used instead. When we call this function, we also use the sigil after the function's name. And that's pretty much all we need for today. Our final draft program in Julia didn't require any advanced structures or date handling, since we reduced all that to simple arithmetic. So let's write our real calculation in QBASIC. We start by initializing our year, month, and day variables, as well as our total count. Note that comments in QBASIC are indicated with an apostrophe and go until the end of the line. Then we begin our main loop. Inside, we add 7 to the current day. QBASIC doesn't have compound assignment operators, so we write this out in full generality. Then we figure out how many days the current month has. Note that QBASIC's select case statement allows us to group multiple cases together by separating the discriminants with commas. In any case, if the day is beyond the end of the month, increment the month and do our check for the first day of a month. Next, check if the month has overflowed, and if so, increment the year. Finally, print the total. And there you have it. This has been a whirlwind introduction to QBASIC. We'll explore some other basic dialects in the future, but this program solves Project Euler problem number 19 in QBASIC. Tune in next time when we take a look at problem 20 in Pyth, a procedural golfing language which compiles to Python.